Now, the first basic point we need to learn here is about flux MMF relation. So we know that, see, I will keep one point in mind. You have studied these basics already in transformers course or DC machines course, okay? And the same basics I am using once again, so that's why I am going a little quickly. So the first relation is flux MMF relation. We know that flux is always equal to MMF by a reluctance of the magnetic medium, okay? And it is Webers. And here MMF is nothing but magnetomotive force. That's why we will use a letter F to indicate it. So in our course, whenever I write letter F, that indicates MMF, magnetomotive force. And what is MMF is equal to number of turns into current passing through those turns, and the unit will be ampere turns. Okay. So magnitude of the flux depends upon MMF, and MMF depends upon number of turns as well as current carried by those conductors. Okay. And what is mean by reluctance? Reluctance is nothing but the physical property of the magnetic medium which will oppose the flow of field flux, right? Okay, it is opposition for flux. And what is the formula for reluctance? It is length by mu into cross-sectional area. Yes or not? Okay, so length by mu into cross-sectional area, and unit will be Henry inverse. Okay, where mu is nothing but permeability of magnetic medium. Suppose if you wanted to show less opposition for flux, permeability should be higher value. To offer higher permeability, we will generally use silicon steel magnetic core. Understand? Okay, we will go much detail in the construction part of the synchronous machine. Okay. So these are the basic formulas which are very much required to understand rotating electrical machines easily. Now let us quickly move into what are the different types of EMFs we have and how Faraday's laws are going to be utilized to understand EMF concepts is the next discussion. Now let us see what are the different types of induced EMFs. We study already in earlier machines course. There are three types of induced EMFs possible. Those are dynamically induced EMF, and second one is rotational induced EMF, and third one is statically induced EMF. Okay, so these are the three types of induced EMFs that we have. Now let us discuss about each type of induced EMF more in detail. Okay, now see, dynamically induced EMF. Yes, what is the definition for dynamically induced EMF? According to Faraday's law of electromagnetic induction, whenever a conductor is moving in a time invariant magnetic field, it experiences changes in flux linkages so that an EMF will be induced across it. So it is all about time invariant magnetic field. Okay, and what is the magnitude of that induced EMF? The magnitude of this dynamically induced EMF is BLV sin theta, where theta is the angle between magnetic field and conductor movement. Suppose if this angle is equal to 90 degrees, maximum EMF will be induced. If that angle is equal to 0 degrees or 180 degrees, there won't be any EMF. And most importantly, what kind of magnetic field we need to use to induce dynamically induced EMF? Time invariant magnetic field. That is important. Okay, time invariant magnetic field. So the name itself is indicating time invariant magnetic field means the magnitude of a flux is going to be constant with respect to time. So if I take flux or flux density on y-axis, and if I take the time on x-axis, the magnitude of the flux is going to be constant with respect to time. So this kind of magnetic field is called as time invariant field. In this time invariant field, if a conductor is moving, definitely it will experience changes in flux linkages so that an EMF will be induced across it. Okay, right. Now, how to create a time invariant field? Very simple. As we know, flux is equal to MMF by reluctance. for a given number of turns and for a given reluctance of the magnetic flux path, flux is directly proportional to current. Suppose if we wanted to create a DC flux which is time invariant in nature, indirectly we need DC current excitation. These are all the things you studied already, I am just recapitulating. So by using DC current excitation, we can create a time invariant field. In that time invariant field, try to move a conductor so that induced EMF will be produced. Now let us see how this dynamically induced EMF can be observed in rotating electrical machines. Okay, let's see. Okay. Now see here, suppose let us assume that we have a two-pole magnetic system. Okay, there is a north pole here and there was a south pole here. Flux is always flowing from north pole to south pole. And assume that these two poles are excited using DC current, so therefore time invariant field will be available. And a number of flux lines will be available between these two poles. Let me mark the names for these flux lines: phi 1, phi 2, phi 3, phi 4 and phi 5. And imagine there was a conductor located inside this magnetic field, and assume that conductor is moving using mechanical prime mover. Okay, assume there was a conductor here. If this conductor is moving in upward direction, what is the angle between flux lines and conductor movement? 90 degrees. In a 90 degrees case, maximum EMF will be induced. That is known for us. Understand? Okay. And yes, 90 degrees. So maximum EMF will be induced. Suppose if the conductor is moving in this direction, can I say the angle between flux line and conductor movement is going to be 0 degrees? In that case, induced EMF is equal to 0. These are all the things you know already. Now the question here is that what is the order of the flux linkage here? Presently, the conductor is linking flux line number phi 3. Next it will link phi 4. Next it will link phi 5. So therefore the order is phi 3, next phi 4, next phi 5. This is the flux linkage order. Now a similar kind of dynamically induced EMF can be produced in one more way also. Look at this. Suppose assume we have another system where two poles are available, north pole and the south pole. Same number of flux lines are there. Okay, this is phi 1, phi 2, phi 3, phi 4 and phi 5. And imagine there was a conductor located on the third flux line, but this time conductor is not moving, rather than conductor magnetic field is moving. Let us assume that conductor is stationary, but these two poles are moving in downward direction with a velocity v. Okay. In the previous case, conductor is moving in upward direction with a velocity v, but in the present case, poles are moving in a downward direction with a velocity v. So you can understand here that in the first case, conductor is moving, magnetic field is stationary. In the second case, conductor is stationary, magnetic field is moving. And you tell me here, flux lines are moving in downward direction means what is the order of the flux linkage? Presently, which flux line is linking this conductor? Phi 3. Next time, phi 4 will come down and link this conductor. Next time, phi 5 will come down and link that conductor. So therefore, what is the order of the flux linkage? I can write phi 3, next phi 4 and then next phi 5. So in both cases, the order of the flux linkage is same. Therefore, same kind of EMF will be induced in both cases. So that means our observation is a conductor moving in upward direction is equivalent to a magnetic field moving in downward direction. You understand that? But in case of rotating electrical machine, we will never study about movement of conductor in upward and downward direction. We will always talk about clockwise and anti-clockwise directions. So from this concept, I can understand that a conductor moving in clockwise direction is equivalent to a magnetic field moving in anti-clockwise direction. Suppose if I gave you a question, conductor is stationary, magnetic field is rotating in clockwise direction, that case is very similar to magnetic field stationary but conductor moving in anti-clockwise direction. Okay, both are similar. Now, in both cases, what kind of EMF is induced? Dynamically induced EMF. Why? Because magnetic field is time invariant in nature. Okay. So, but what is the difference here? Who is stationary and who is moving here? Magnetic field is stationary. This conductor is moving. This is what we will use in case of DC machine. Okay, in case of DC machine, either DC generator or DC motor, in both cases, magnetic field will be stationary, armature conductor is moving. But here, armature conductor is stationary, but magnetic field is moving. This is what we will study in case of synchronous machine. Except that there is absolutely no difference between a DC machine and AC machine. Both machines are working on the same principle. What is that? Faraday's law of electromagnetic induction. Both machines require the same magnetic field. What is that? Time invariant magnetic field using which current excitation? DC current excitation. That's why in DC machine and synchronous machine, we will excite field system using DC current always. Okay. But what is the difference? Who is stationary? That is stator, and who is moving? That is rotor. Yes, in case of DC machine, the stationary one is magnetic field and the moving one is armature conductor. Okay. Coming to synchronous machine, what is stationary? That is nothing but stator. Yes, in case of synchronous machine, armature conductors are stationary, and coming to the moving part, that is the rotor part, magnetic field is going to be the moving part. Except that there is no difference. Now, the next question is, which is the easiest procedure here? We know that synchronous machine is going to be the easiest procedure. Why? Because in case of synchronous machine, armature winding is stationary in nature. What are the advantages if a winding is stationary? When a winding is stationary, collecting the current from that winding is easy. Also, supplying the current to that winding is also easy. Suppose if you consider a DC machine, armature conductors are continuously rotating in nature. When winding is continuously rotating, how to tap the current from that winding? It is very difficult. Arcing and sparking problems will be there. Okay, that's why synchronous machine is going to be an arcless machine. DC machine will have arcing problems because armature winding is rotating in nature. Even though DC machine has arcing problems, why we are still using rotating conductors only? The reason is to satisfy commutator and brush action. We know that DC machine will use commutator and brush system. To satisfy that commutator and brush system action, we need rotating armature. But whereas a synchronous machine does not require commutator and brush system, so therefore better to use stationary armature winding. What are the advantages of stationary armature winding? Collecting the current, supplying the current is going to be very easy without any arcing. There are other advantages also we will discuss in the construction part of the machine. So these are the two major differences between DC machine and synchronous machine. But remember, in both machines we are using time invariant magnetic field using DC current excitation, and both machines will work based on Faraday's law of electromagnetic induction. Okay. Now let's try to solve a simple example question. This question was repeated in many state level services exam and even in PSU exams also. One time the question came in GATE examination as well. Okay, let's see. Alright. Now look at this question. We have a 4-conductor magnetic core, and there was a rotor having 2 poles. And if you clearly look at the diagram, the conductors are rotating or the poles are rotating? Yes, the poles are rotating in anti-clockwise direction at a speed omega radian per second, and we are asked to find out what is the polarity of EMF in each and every conductor. I told you already here, conductors are stationary, magnetic field is rotating. In which direction magnetic field is rotating? Anti-clockwise direction. Now, how to find out the polarity of induced EMF? As you studied already in case of DC machines, I told you that polarity of induced EMF can be identified using Fleming's right hand rule. I hope I need not to explain again about this. In Fleming's right hand rule, this thumb point finger and central finger must be placed in a mutual perpendicular direction. What thumb indicates? Thumb indicates the direction of conductor movement. Point finger will indicate direction of magnetic field. Central finger will indicate the direction of induced EMF in the conductor. Now, as I told you, thumb indicates the direction of conductor movement, but here the conductors are not moving. Then how to utilize the Fleming's right hand rule? Yes, that is what I said. I told you that magnetic field moving in anti-clockwise direction is equivalent to conductors moving in clockwise direction. So therefore what I can do here is that I can assume these field poles are stationary and conductors are moving in clockwise direction. Yes, this case is very similar to the previous case, right or not? Okay. Now, yes, tell me, find out the polarity of induced EMF in each conductor. Yes, this is north pole. So north pole will emit the flux, right? So point finger will show you the direction of flux. Conductor is moving in clockwise direction, that means to the right side. Now what my central finger is showing, this is showing out of the plane or into the plane? Out of the plane. Therefore the polarity of conductor 1 is dot. Coming to conductor 1 dash, this is under south pole. South pole means it is emitting the flux or taking the flux? Taking the flux. Conductor is moving to the left side clockwise. So my central finger is showing into the plane, therefore it is going to be a cross polarity. And moreover, this EMF is maximum and this EMF is also maximum. How can you say the EMFs are maximum in these two conductors? The reason is these two conductors are along polar axis of the machine. I hope you remember what is meant by polar axis, what is meant by interpolar axis. What is meant by polar axis? It is the axis along which induced EMF is maximum. And why the name is given as a polar axis? The reason is it is passing through the two poles, right? And you can also call polar axis as with another name, that is nothing but direct axis also, D axis. Polar axis or direct axis, both are same. That is the axis along which induced EMF is maximum. Now what is meant by interpolar axis or quadrature axis? Yes, perpendicular to polar axis. This is what we will call it as interpolar axis, also called as quadrature axis. Quadrature axis or Q axis. What is meant by quadrature axis? It is the axis along which induced EMF across the conductor is equal to 0. Therefore, induced EMF in second conductor, induced EMF in 2 dash, in both these conductors the induced EMF is equal to 0. Maximum EMF will be induced across a polar axis, 0 EMF will be induced across interpolar axis. So this is the way to find out the polarity of induced EMF. Okay. Now let me give you one more question. Okay. Take it as a practice. Alright. Now look at this question. Once again we have a two-pole magnetic system and the poles are rotating in clockwise direction. So therefore conductors are stationary and the magnetic field is rotating. Now how to find out polarity? To find out polarity I need conductor movement direction. But physically the conductors are not moving here. So therefore you can take relative movement. So we know that a magnetic field rotating in clockwise direction is equivalent to conductors rotating in anti-clockwise direction. So therefore I can treat magnetic field is now stationary and the conductors are rotating in anti-clockwise direction like this. Okay. So now identify the polarity of EMF across direct axis first. I know direct axis means it is the axis passing through the poles. This is going to be D axis. If this is D axis, exactly perpendicular, we have Q axis. Okay. Now above this Q axis, which pole effect? North pole effect. Below this Q axis, which pole effect? South pole effect. And along Q axis, is there any conductor? Yes. According to the given diagram, there is no conductor along Q axis. So you can understand here B dash, A and C dash are under the effect of north pole and C, A dash and B are under the effect of south pole. Out of them, A and A dash will experience maximum EMF because they are along D axis. This B dash, C dash are away from D axis, therefore they will experience induced EMF but not maximum, okay, less than maximum. So let us see how to find out the polarity of induced EMF. This is north pole emitting the flux. Now see, conductor is moving in anti-clockwise direction. See the direction of conductor movement. Now my central finger is showing into the plane, so therefore cross polarity. Therefore these two conductors are also experiencing cross polarity. Why? Because these three are under the effect of north pole. But only which conductor will experience maximum EMF? Conductor A only. So let me draw with some thick line, thick cross. That indicates maximum. These two are experiencing less than maximum EMF. Now obviously you can understand A dash will experience a dot polarity, but a thick dot indicate maximum EMF. C and B will experience less than maximum, so that's why I put some smaller dot. Okay. Suppose if I gave you two more conductors here, they will experience zero EMF. Understand? Okay. So this is the way to find out the polarity of induced EMF. Either conductor is moving or magnetic field is moving. Okay. Now let's talk about rotational induced EMF. In case of dynamically induced EMF, we understood that if a field is stationary, conductor is moving. If a conductor is stationary, field is moving. But in rotational induced EMF, both field as well as conductor are moving at the same time. So see here, this discussion is over already in DC machines. I am just recapitulating. That is what I told you already. Suppose we have a north pole and we have a south pole here. Number of flux lines will be there. Okay, look at this. I am assuming 5 flux lines. Phi 2, Phi 3, Phi 4, Phi 5. Assume there was a conductor located on Phi 3 line. And imagine this conductor is moving in upward direction at a velocity of V meter per second or V1 meter per second. Suppose in case if a magnetic field is also moving in the same direction with the same velocity, then what happens? Conductor is moving with V1 velocity, magnetic field is also moving with V1 velocity, therefore always the conductor will link Phi 3, there won't be any change in flux, there won't be any induced EMF. That's why to induce EMF, conductor and magnetic field must rotate or must move with the same speed or different speed, Suppose imagine magnetic field is moving with a velocity V1, conductor is moving with a velocity V2, then definitely there is some relative difference between the speeds, therefore induced EMF will be produced. Okay, so that's why when both are moving, when field and conductor both are moving, the induced EMF is proportional to relative speed between magnetic field and conductor. This is what we will study most of the times in case of induction machines. However, in synchronous machines also we will come across this induced EMF, especially in damper winding. Okay, when we come to that particular concept, you will understand. Okay, so especially when this EMF will come into picture, field is moving, conductor is also moving, but with different speeds. Suppose magnetic field is moving with a synchronous speed ns. Let us assume conductors are also moving with the same synchronous speed ns. Then what is the relative speed is equal to 0. If relative speed is 0, obviously induced EMF is equal to 0. Okay, so this concept we will study in synchronous machines, especially about damper winding and hunting problems. Okay, yes, when hunting phenomena concept came into picture, we will come across this rotational induced EMF. Okay, we discussed about more details regarding this EMF already in DC machines course. Okay, you can open your notes once again. I took some examples like 10 meter per second, 12 meter per second, like that. Okay. So when field and conductor both are moving, the relative speed between the two is important. It is the relative speed between a magnetic field and the conductor. We will study in synchronous, mostly in induction machine, but a part of this we will study in synchronous machine also, especially when hunting phenomena takes place. Okay. Now so far whatever the basic concepts I revised, we have already studied. Now this is the first topic we are studying regarding synchronous machines, that is basics of electromagnetic torque concept. This concept is applicable for synchronous machine, induction machine and also for DC machine. Okay, right. So to understand this electromagnetic torque concept, let me take some simple examples first. Now imagine we have a rotating electrical machine. Let us assume this is the stator part of the machine, and assume that this stator has let us say two poles, okay, north and south poles. And inside this stator, let us assume we have a rotor part also, and assume this rotor is designed with 4 poles like this, right? So this should be north. So concept is simple. Stator has 2 poles but rotor has 4 poles. Now the question is, in which direction the rotor is going to rotate? We know that when 2 opposite poles are there, there will be force of attraction, and when 2 similar poles are near to each other, there will be force of repulsion. Apply that concept simply. See, here we have a north pole, we have a south pole here. So between these two, attraction force will be there. Therefore this south pole will be attracted towards this north. And here you see this is north and this is north, there will be a force of repulsion. So this north pole will be pulled away from this north pole. So therefore these two poles are experiencing the force in which direction? Anti-clockwise direction. Coming to these two, we have a north pole here and we have a south pole here. Therefore north pole will be attracted towards this south. And we have a south and south here. This south pole will be repelled by this south. Now you tell me these two poles are experiencing force in which direction? Clockwise direction. These two poles are experiencing the force in which direction? Anti-clockwise direction. Therefore, the average force or average torque acting on the rotor becomes 0. Okay, I can write the average torque is equal to 0. This is anti-clockwise, this is clockwise. Both will cancel each other. Average torque is equal to 0. If average torque is equal to 0, the rotor can rotate or cannot rotate? Obviously cannot rotate. So therefore, what is our observation? When a stator has 2 poles, rotor has 4 poles. That means number of poles are not equal in stator and rotor. In that case, average torque will be equal to 0. Understand? That's why let us move to the next case where I will consider same number of poles in stator as well as rotor. Okay, see here. Now look at this. Assume this is the stator part of the given machine, and assume this stator has 2 poles, north pole and south pole. Inside this there was a rotor. Let me draw it more clearly. Yes, this rotor also has 2 poles. Now stator and rotor has the same number of poles. Now tell me what is the direction of torque or direction of force? You can understand. This is north pole, this is south pole. Obviously this south pole will be attracted by this north. This is north pole and this is south pole. This north pole will be attracted by this south. Now you tell me both forces are in the same direction, that is clockwise or anti-clockwise? Anti-clockwise. Therefore average force existed. Automatically the rotor started to rotate because of that force. In which direction the rotor is rotating? Anti-clockwise direction. But once the rotor started to rotate, can you tell me what happens after 1/2 cycle? 1/2 cycle means, can I write 180 degrees? Yes or not? After 1/2 cycle, I can say this north pole will come to this location. This south pole will come to this location. So let me draw a new picture. So this is the stator we considered stationary. Stator has 2 poles. Now rotor rotated by exactly 1/2 revolution. Half revolution means this north pole will go to this location and south pole will come to this location. Now tell me what is the direction of force experienced by rotor? This is north and this is north. There will be a force of repulsion. Therefore, it will be pulled away. This is south and this is south. There is a force of repulsion. This will be pulled away. Now tell me what is the direction of force experienced by the rotor? It is anti-clockwise direction or clockwise? Clockwise. So for the first half cycle, the force is in anti-clockwise direction. For the next half cycle, the force is in clockwise direction. Therefore, what happens to the average force or average torque acting on the rotor? Once again, the average torque acting on the rotor becomes 0. Why? Because for one half cycle clockwise, for another half cycle anti-clockwise, both will cancel each other. Average torque becomes 0. Therefore, rotor cannot rotate. So, in the first case, poles are not equal. That's why torque is equal to 0. But in the second case, stator and rotor has the same number of poles, but still average torque is equal to 0. The rotor cannot rotate. So, what to do now? So, both cases failed. So, that's why let me move to the third case, which is going to be a successful case where we will get finite average torque and the rotor will continue to rotate. Okay, let's see. Alright. Now, let me take the third case here. Once again, I am taking a simple diagram here. Assume this is the stator part of the given machine, and assume this stator has two poles, north pole and south pole. Inside this we have the rotor part, and I am taking two poles in rotor again, south and north, same number of poles. Now tell me first, what is the direction of force acting on the rotor? Initially some force will definitely act. What is the direction of force? Yes, this is north and this is south, attraction force is there. This is north and this is south, attraction force is there. Therefore I can say the force acting on the rotor is in anti-clockwise direction. Because of that force, can I say rotor will definitely start rotating initially? And whenever I said the rotor poles are rotating, that rotation will have some speed definitely. And assume that speed is equal to 10 RPM. This is just example. You take randomly whatever speed you want. Assume the rotor poles are rotating with 10 RPM. Now imagine what happens if stator poles are also rotating in the same direction with the same speed 10 RPM. I said very clearly, rotor poles are rotating with 10 RPM. Now imagine stator poles are also rotating in the same direction with the same speed. I said stator poles are rotating, not stator. Stator means it is a stationary body, it won't rotate. But stator poles are rotating. Now can you tell me what happens after half revolution, that is 180 degrees? After half revolution, can I say this north pole will come to this location and south pole will come to this location? Similarly on the stator also, south pole will come to this location and north pole will come to this location. Therefore let me draw the second diagram. Stator body is stationary, but stator poles are rotating by 180 degrees. Therefore south will come here, north will come here. Now coming to the rotor, after 180 degrees, that is half revolution, north will come here and south will come here. Why both stator and rotor poles are rotated by the same angle? Because both are rotating with the same speed. That is important. Okay. Now can you tell me what is the direction of force acting on the rotor? This is south and this is north, force of attraction. This is south and this is north, force of attraction. Can you tell me once again what is the direction of force acting on the rotor? Clockwise or anti-clockwise? Anti-clockwise. In this case also, what is the direction of force acting on the rotor? Anti-clockwise. Both forces are in the same direction, means average torque will be a finite value or zero value? Finite, and the rotor continue to rotate. Okay. Average torque is a finite value here. So therefore, what is our observation here? In order to produce a finite torque on the rotor, what are the conditions to be satisfied? First condition, stator and rotor should have same number of poles. In case if number of poles are not same, definitely the rotor cannot rotate. First condition. Second condition is, you see here, stator poles are rotating with 10 RPM in anti-clockwise direction. Rotor poles are also rotating with 10 RPM in anti-clockwise direction. Both poles are rotating in same direction with the same speed. Therefore, what is the relative speed between these two? 0. Am I right? If two objects are moving in the same direction with the same speed, the relative speed between the two becomes 0. So therefore, the second condition to be satisfied here is the relative speed between stator poles and rotor poles must be equal to 0. Relative speed between poles means, can I say simply relative speed between fields, because poles will create magnetic field. Therefore, the second condition is the relative speed between stator magnetic field and rotor magnetic field must be equal to 0. This is very crucial and it is true in case of DC machine, synchronous machine, induction machine also. So what are the conditions to be satisfied? First condition, stator and rotor should have same number of poles. Second condition, relative speed between stator magnetic field and rotor magnetic field must be equal to 0. Okay, let me write down these two. Stator and rotor must have same number of poles. Second condition is relative speed between stator magnetic field and rotor magnetic field must be equal to 0. Now, these are the two conditions we studied so far. There is a third condition also that we have to show with a theoretical proof. Let me write down here, then we will see what is the theoretical proof for that. Okay. The third condition is phase angle between stator field and rotor field must be finite. Phase angle The third condition is the phase angle difference between stator field and rotor field must be finite. So clearly understand the difference. In the second point we are talking about relative speed, that should be 0. Third point we are not talking about speed, we are talking about phase angle difference, that should be finite. If it is 0, torque cannot be produced. So how can you understand the third point is our next discussion. Okay. So for first our observations are stator and rotor should have same number of poles. That means stator will have one field, rotor will have one field, and both fields should have same number of poles. Second thing is the relative speed between these two fields must be equal to 0. Third point is the phase angle difference between these two fields must be finite. Let us see why. Alright, now see here. Assume we have a stator magnetic field here. I told you MMF is represented by a letter F. F indicates MMF. And F1 is nothing but stator MMF. And we have a rotor MMF also. Assume F2 is rotor MMF direction. And these two are differed by a phase angle lambda. Okay. Lambda is the phase angle difference between stator magnetic field and rotor magnetic field. So when there is a phase angle difference between these two, then what is the resultant MMF is going to be? It is a vectorial summation. Okay. It will be definitely in between these two. This is resultant MMF, also called as air gap MMF. Okay. Air gap MMF or resultant MMF, any word you can use, and let me represent with the letter FR. So can you tell me what is the summation of two vectors differed by a phase angle lambda? So we know that resultant MMF is equal to square root of F1 square plus F2 square plus 2 F1 F2 cos of the angle between these two. This is a vectorial summation. But our requirement is not MMF equation here. Our requirement is the torque equation. So don't ask me questions or F indicates force. I am repeating once again. Here F indicates MMF, magnetic field, magnetic MMF. Now our requirement is to develop the equation for a torque here, not about MMF. So to understand the equation about torque, let me first understand what is the medium between stator and rotor. Air medium. In that air medium we have electromagnetic field or electrostatic field, electromagnetic field. Can you tell me the formula for energy stored by electromagnetic field? We know energy stored by magnetic field is equal to half Li square. Yes or not? And we also know the formula for inductance L. Can I write L is equal to N square by R? Yes, we studied many times. Therefore, I can write half into, if you look at the numerator, we have Ni square by R. What is mean by Ni? That is nothing but MMF, especially resultant MMF. So therefore, this is half into resultant MMF square by reluctance. This is the energy stored in a magnetic field. But we know that once the construction of the machine is completed, reluctance is going to be a constant value. If I include all the constants in proportionality, then energy stored will be proportional to MMF square. I am including these constants into proportionality. We know already expression for resultant MMF, but energy is proportional to square of the MMF. So let me continue here. So therefore, what is the energy? Energy is proportional to square. Square means root will cancel. F1 square plus F2 square plus 2F1 F2 cos lambda. That is the energy equation we have. But our requirement is energy equation or torque equation? Torque equation. So for that purpose, I would like to use the basic kinematics definition. See, just understand. Suppose I have an object in my hand. I wanted to move this object from one location to another location. So to move this object, I have to create some force on this object, then only it will move. To create that force, I need to spend some energy or no need to spend any energy? Yes, I need to spend some energy, then only that energy will be converted into force and that force will move this object. That's why the basic definition for force is, I can write here, the basic definition for force is, it is the amount of energy that we spent, dE, amount of energy that we spent to move the object by a finite distance of dx meters. Dx is the small distance by which the object is moving. There is an object. Using the energy you have, create some force on this object. Therefore, this object will move some distance. If you wanted to move more distance, you need more force. That means you need to spend more energy. That's what. Now, the same concept can be implemented in our rotating electrical machine also. In rotating electrical machines, our conductors will move in linear direction or angular direction. Angular direction. Therefore, force is denoted by torque. Okay. So, torque is nothing but the amount of energy that we spent to move the conductor by a finite distance of meters or a finite angle of radians. As it is rotating electrical machine, conductors will move angularly. So, torque is nothing but the amount of energy that we are spending to move the conductor by a finite angle, and that angle is nothing but lambda. Okay, lambda. To move the angle by a finite angle d lambda. So, this is the basic equation for torque. Already we have energy equation. So I can say torque is now looking like differentiation for energy equation with respect to lambda. So I can write torque is proportional to, yes, can you tell me proportionality I am writing, there are so many constants, don't forget. Yes, what is the differentiation for this equation with respect to lambda? When I am differentiating with respect to lambda, f1 square differentiation becomes 0, f2 square differentiation becomes 0, cos lambda, what is the derivative? Minus sine lambda. 2 is a constant, I can include in proportionality. So what is the final equation for torque? Minus f1 f2 sine lambda. There is 2, but I am including in proportionality. So cos lambda differentiation is minus sine lambda. So this is the final equation for electromagnetic torque. I can say basic expression. So what F1 is here? F1 is stator MMF. F2 is rotor MMF. And what is the lambda here? Lambda is the angle between stator MMF and rotor MMF. Okay. Now just imagine what happens if stator field and rotor field lies on each other. If stator field and rotor field lies on each other, can I say the angle lambda becomes 0 if both fields lies on each other? If lambda is equal to 0, then what will be this? Sine 0 becomes 0. In that case, torque can produce or cannot produce? Cannot produce. That is the third point I told you. What is the third point for the production of torque? The phase angle difference between stator field and rotor field must be finite angle. In case if this angle is equal to 0, then the torque is equal to 0. Imagine if this angle is equal to 90 degrees, what happens if angle between stator field and rotor field is 90? We know sin 90 is maximum torque can be created. If angle is equal to 0, torque cannot be created. Okay. And one more point you need to understand, there is a negative sign in this torque equation. This is crucial. This negative sign is indicating the existence of Lenz's law. We studied many times. In every electrical machine we will study about Lenz's law. That negative sign will indicate Lenz's law. What Lenz's law states that effect will always try to oppose the cause of the production. Oppose means it will try to reduce the cause. Reducing the cause. Here, what is the cause for the production of torque? Finite lambda or 0 lambda? Finite lambda. So therefore, effect is the torque. The reason is this lambda. So therefore, what this torque will try to do? It will try to reduce this lambda. So that is how you need to understand Lenz's law here. The torque is produced because of lambda, angle lambda. If lambda is 0, definitely torque is equal to 0. Therefore, this is cause here and this is the effect. And this effect will try to reduce the cause. Therefore, in rotating electrical machines, whatever electromagnetic torque is produced, it is always trying to reduce this angle lambda. Trying to reduce. But really, if it is reduced to 0, torque also becomes 0. So, torque will always try to reduce, but it will never be able to reduce it to 0. Now, answer my question here. The torque is always trying to reduce this lambda means indirectly electromagnetic torque is trying to align these two fields each other or trying to make these two fields away from each other. Yes. Reducing lambda means these two fields are trying to align with each other. Okay. They wanted to align with each other because of the attractive force, but they will never align. In case if they align with each other, torque becomes 0. Okay. So this is about basic concept of electromagnetic torque. So just revise once again the summary point here. What are the conditions to be satisfied for the production of electromagnetic torque? First condition, stator and rotor should have same number of poles. Second condition, stator field and rotor field, the relative speed should be 0. Relative speed means, suppose if a stator field is rotating in anti-clockwise direction at a speed ns, synchronous speed, we will study very soon. Then rotor field must also rotate in the same direction with the same speed. In that case, what is the relative speed between these two? 0. If a stator field is rotating with the ns speed, rotor field also rotating with the ns speed, then the resultant field will also rotate with how much speed? Ns. Why? Because it is always in between the two. So in AC machines especially, stator field, rotor field will rotate with the same speed in the same direction, therefore relative speed is 0. In that case, resultant field will also rotate with the same speed in the same direction. Understand? And the third condition is, phase angle difference between stator field and rotor field must be a finite angle. In case if that angle is 0, torque cannot be produced. And this torque equation is valid for synchronous machine as well as induction machine and even for DC machine also. Okay.